Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module Toughening Mechanisms from the paper Ceramics. So the learning objectives of this module are: first, flaws in ceramics by first the pores, second agglomerates, third inclusion, and fourth by large grains will be discussed. Secondly, the surface flaws by grain boundary grooving during the sintering, and machining and handling damage will be discussed. Next, the toughening mechanism will be discussed. Lastly, the crack tip interactions will be discussed. Next, we will also discuss the crack tip shielding by transformation toughening and micro crack formation. Then we will also discuss about the toughening by crack bridging. So students, let us start with a brief introduction about the module. The fracture of ceramics initiates from pre-existing flaws in the ceramics. So in this module, we first discuss the source of these flaws. Fracture toughness is an important and critical property of structural ceramics. It is generally very low in these materials. So a knowledge of the toughening mechanism materials. Of the toughening mechanism, it is important to design the ceramics with increased toughness. So this is the thing which we are going to discuss in this module. Flaws in ceramics. First, pores. The ceramics are manufactured by powder processing. This process invariably leads to the presence of some porosity. The pores in the ceramics are a major source of flaws. In addition, there may be flaws on the surface which can be introduced later during machining or during service. So, pores, the strength and the porosity of the pores have been found to be related by the following relation, that is sigma p equal to sigma naught exponential minus bp, where sigma p and sigma naught are the strengths with and without the pores respectively. P is the volume fraction porosity and B is a constant which depends on the morphology and distribution of pores. So the severity of the pores increases the manifolds if it is near other flaws. For example, if there is a cusp of a grain boundary next to a pore, then the cusp and the pore become one big flaw with the sharpness of the cusp and the sizes of the pore as shown in this figure. Next type of flaw in ceramics is agglomerates. A cluster of particles in the starting powder is called an agglomerate. It may be a soft agglomerate in which the particles are bonded softly together, or may be a hard agglomerate in which the particles are bonded by the formation of strong bond between the particles during calcination or other processing step. So during sintering, the soft agglomerates densify much more than the rest of the powder compact, while the hard agglomerates densify very little. This causes the generation of stresses which leads to the flaws. So this figure on the left hand side, the part A shows a slow sintering inclusion, the shaded, is surrounded by a fast sintering matrix. This generates a hoop stresses causing radial cracks. In the part B, a faster sintering inclusion is surrounded by a slower sintering matrix. In this case, a tensile stress is produced at the interface, producing circumferential cracks. The next type of flaw in ceramic is inclusions. Inclusions having different chemical composition that the matrix may form in a ceramic during sintering due to chemical reactions of the impurities with the powder. An inclusion will in general have a different thermal coefficient of expansion than the matrix. So on cooling from the sintering temperature, the two will contract to different amounts. Below a certain temperature, the stresses will not be able to relax, and so the flaws will form in a manner similar to the case of agglomerates. The stresses produced at a distance r from the inclusion are given by the expression sigma rad equal to minus 2 sigma tan equal to alpha m minus alpha I multiplied by delta T divided by 1 minus 2 nu I by EI plus 1 plus nu m multiplied by 2 EM. This is multiplied by R by small r plus R the whole cube. Here sigma rad and sigma tan are the radial and tangential stresses respectively. Alpha m and alpha I are the coefficients of thermal expansions. Nu m and nu I are the Poisson's ratio. Em and Ei are the Young's moduli of the matrix phase and the inclusion respectively, and R is the radius of inclusion. Now delta T is the difference between the initial and the final temperature during cooling. So it can be seen that the stresses produced are directly proportional to delta T and vary as the cube of the size of the inclusion. Flaws in ceramics by large grains. Exaggerated grain growth may occur during sintering in some cases. The large grains have anisotropic thermal coefficients of expansion and elastic moduli and act as inclusions with respect to the surrounding matrix, leading to the generation of flaws similar to the case of inclusions. So let us now discuss the surface flaws, and the surface flaws in a ceramic can arise from various reasons. Let us first discuss the first reason, that is grain boundary grooving during sintering. Some of the grain boundaries are exposed to the surface, so the sublimation of the material occurs at a more rapid rate from the exposed grain boundaries. This causes the formation of grooves at the grain boundaries as shown in this figure. These grooves act as the flaws. Also, the surface cracks can propagate along these grooves. Let us now discuss the second reason for the surface flaws as machining and handling damage. Ceramic components are usually subjected to finishing operations such as grinding, polishing. The grinding particles act as indenters and produce surface damage. The indents produced may propagate along the grain boundary or through the grain along the easy cleavage planes as shown in this figure. These cracks usually stops at the grain boundary. So during service also some surface damage may be introduced, which also behaves in a similar fashion. So the cracks due to surface damage have therefore a size of the order of the grain size. So let us now discuss the dependence of the strength on grain size. As discussed above, the flaws produced due to surface damage scale as the grain size. So as the strength is expected to vary as c to the power minus half, where c is the half crack length, the strength is expected to decrease as the grain size increases. This is found to be true in practice. So the figure over here shows schematically the change in the strength with the grain size. So at a very small grain size, the surface flaws are larger than the grain size to start with, and so the strength becomes nearly independent of the grain size as shown in this figure. Toughening mechanisms in ceramics. So the fracture toughness of ceramics is generally quite low. So this table compares the fracture roughness of ceramics and other materials. Let us now discuss the toughening mechanism. The fracture toughness of ceramics is generally quite low. So we need to design the microstructure to improve the toughness. Toughness depends on the energy consumed during crack propagation. So any microstructural feature which impedes the crack propagation requiring more energy consumption for crack propagation, or any process which introduces stresses which opposes the applied stress would lead to an increase in the stress intensity factor. So on this basis, the mechanisms for toughness increase can be categorized broadly into the following categories. First, the crack tip interactions. Second, crack tip shielding. And third, crack bridging. So let us now discuss the crack tip interactions, crack bowing. A common method of toughening of the ceramics is to incorporate the second phase particles, fibers, whiskers or other features which act as the obstacles to crack the propagation. The crack may respond to the presence of these obstacles in two ways. It can continue to move by bowing between the obstacles, or it may get deflected. So the mechanism of crack bowing is shown in this figure. The crack goes around the particles and then joins back again. The particles remain unbroken, and the calculations shows that this leads to an increase in the fracture roughness. Crack tip interactions, that is crack deflection. In crack deflection, the crack is deflected out of the plane on which it is propagating. So the applied stress is now no longer normal to the crack plane, and so its effectiveness decreases. The crack may just tilt with respect to the crack front, or it may twist or both. So this figure shows schematically the crack deflection at obstacles by crack tilting. So there is an increase in the toughness due to crack deflection. The crack twisting leads to higher increase in toughness than crack tilting. The fracture surface becomes rough as a result of crack deflection. Now, as the analysis of the crack deflection process shows that the crack growth resistance increases first with the volume fraction of the second phase particles, which provide the obstacles but then becomes constant. Also, the shape of the particles is very important. The rod-shaped particles are most effective, followed by the disc-shaped particles, least increase being due to the spherical shaped particles. This is shown schematically in this figure, where the toughening by crack deflection Tc is the toughness of the composite and Tm that of the matrix. So toughening increases with the volume fraction of the particles up to certain volume fraction, and the rod-shaped particles are most effective. Let us now discuss the crack tip shielding. The metals have much higher fracture toughness than ceramics. So there is a plastically deformed zone ahead of the crack tip. The stress experienced by the crack tip is reduced, so much less than the applied stress. So in this effect, the measured fracture toughness is higher. The reduction in the stresses at the crack tip due to the plastic deformation or any other process occurring near the crack tip is called as crack tip shielding. So in ceramics, there is hardly any plastic deformation, but there are other processes which can occur and cause a reduction in the stress intensity factor experienced by the crack tip. Now, let us consider Kia is the stress intensity factor according to the applied stress, and KIL is the local stress intensity factor experienced by the crack tip. Then KIL is less than KIA if there is a process zone near the crack tip in which processes which causes a reduction in the stress intensity occurs. So what these processes may be, we will be discussed. So the failure will now occur when KIL equal to T, where T is the toughness of the ceramic. The measured stress intensity factor will be higher by the amount delta K equal to KIA minus KIL. Crack tip shielding by transformation toughening. The two important mechanisms of crack tip shielding in ceramics are first, transformation toughening, and second is stress-induced micro-cracking. Many ceramics can undergo transformation toughening. Transformation toughening is the most pronounced and most well studied in zirconia. The stable phase in zirconia is monoclinic at room temperature. So, however, the high temperature tetragonal phase can be stabilized at the room temperature if particle size is less than a critical size. Second, a stabilizing additive like Y2O5 has been alloyed with ZrO2. So the critical size is increased by alloying. Under external stress, there is a transformation from T to M occurs, 7% shear strain and approximately 4% volumetric strain. This effectively reduces the stress intensity at the crack tip, leading to an increase in the fracture toughness. Crack tip shielding, transformation toughening. So continuing the discussion over it. So stresses near the crack tip causes the T particles to transform to M. So as the crack advances, a wake of the transformed zone is left behind around the crack. So the maximum value of the toughening that can be obtained from the transformation toughening is delta T max equal to C multiplied by E V nu T multiplied by e to the power T multiplied by root of H divided by 1 minus nu. Now here C is a constant, E is the Young's modulus of the matrix, V nu T is the volume fraction of zirconia transformed, Et is the volumetric strain associated with the transformation, 2H is the width of the transformation zone, and nu is the Poisson's ratio. So the tetragonal phase is stable at room temperature below a critical size. Smaller tetragonal particles require a higher stress for transformation. So under given loading condition, the fraction of small particles that transforms increases as the particle size increases, and so the toughness also increases. So after the critical size, the particles are already in the monoclinic form, and so there is no transformation. The toughness therefore decreases after reaching a maximum as shown in this figure. Crack tip shielding by micro crack formation. Micro cracks can form ahead of the crack tip due to the presence of residual stresses. Residual stresses arises if first we have a large grain size and large anisotropy in thermal expansion. Second, in multi-phase ceramics, differences in thermal expansion between different phases. So the residual stresses add to the stress at the crack tip, causing the formation of micro cracks. This results in the relaxation of stresses and so in the crack tip shielding. Increasing grain size implies increasing residual stresses implies increased fracture toughness. So too large a grain size implies very large stresses, implies micro cracks form without external stress, implying decrease in the toughness. Toughening by crack bridging. The phenomena of crack bridging is often observed in large grain-sized ceramics. Some large grains bridge the two crack surfaces behind the crack tip. More than one grain may form frictional interlocking bridges across the two crack surfaces. So these bridges take up the part of the load on the crack tip and thus reduces the effective stress intensity on the crack tip. The measured toughness is therefore increased. So this shows the example of crack bridging. So students, let us summarize what we have learnt in this module. First, the toughening mechanisms in ceramics can be categorized broadly into the following categories. First, the crack tip interaction. Second, crack tip shielding. And third is crack bridging. Next, we discussed about the crack tip interactions occurs when the crack tip approaches an obstacle such as a second phase particle. Next, we discussed that the crack can continue to move by bowing between the obstacles, or it may get deflected. In crack bowing, the crack goes around the particles and then joins back again. The particles remain unbroken. Calculations show that this leads to an increase in the fracture toughness. Next, we discussed that crack deflection, that is, crack deflected out of its propagation plane, implying that applied stress no longer being normal to the crack plane, implying that there is an increase in the toughness. The crack growth resistance increases first with the volume fraction of the second phase particles, but then become constant. Effectiveness of particle shape. Rod-shaped particles, that is disc-shaped particles or spherical-shaped particles. Crack tip shielding. There is a decrease in the stress intensity factor due to some processes occurring in the vicinity of the crack tip. In metals, this process is called as plastic deformation. In ceramics, there is a stress-induced phase transformation and stress-induced micro-cracking, which results in the crack tip shielding. Examples of stress-induced phase transformation is transformation toughening in zirconia and other ceramics. Both the stress-induced transformation and micro-machining lead to very significant increase in the fracture toughness. Now, crack bridging. It is often observed in large grain sized ceramics. Some large grain size bridge the two crack surfaces behind the crack tip. So, more than one grain may form frictional interlocking bridges across the two crack surfaces. These bridges take up the part of the load on the crack tip and thus reduces the effective stress intensity on the crack tip. The measured toughness is therefore increased. Thank you.